Hey guys, so let's start to look at chapter 9 chemistry, penultimate chapter and one of the toughest. It's acid-base chemistry. Excuse me. So again, let's look at our scenarios to whet our appetite for the acid-base chemistry. You're walking around in the ward and you see one of the patients looking very anxious indeed. You find out that they have a big operation the following day, and they start to get short of breath and breathing more rapidly. And so you give them a paper bag and get them to breathe in and out of it for a couple of minutes. And they make a complete recovery and their breathing returns to normal. What exactly is going on here? How does breathing in and out of a paper bag help? And what is it in the paper bag that helps? We'll talk about that in the chapter. You're in a pharmacy working, and a a customer, I guess, comes along looking for some help with acid indigestion. It doesn't look like you have your normal remedies over the counter for antacid tablets, but you have some raw materials you can work with, so maybe you can do them some good. There's sodium chloride, potassium sulfate, aluminium hydroxide at your disposal. Which of these chemicals, if any, could be of help? And what is it about the chemical that you should recognize as a potential antacid? Then we're swimming with a friend, they're practicing holding their breath underwater, and they come back up to the surface complaining of a burning sensation in their muscles. You inform them that they've managed to induce a mild case of respiratory acidosis. What does this mean, and how exactly did they manage to make this happen? That's the kinds of chemistry that we'll be coming across in this chapter. So for our starting point, it might be a good idea to actually do some revision of ion chemistry with our metal and non-metal ions, and also the polyatomic ions that we had talked about then as well. There's quite a lot of ion chemistry in acid-base chemistry. Principally, we want to refresh our memory of two particular ions, hydrogen ions and hydroxide ions. Hydrogen ions, of course, that's just a hydrogen. When it loses its electron, its shell is emptied, and that positive charge from the proton in the nucleus is unchecked. We sometimes refer to these hydrogen ions as protons because without the electron, that's all we have left. There aren't normally any neutrons in a hydrogen, and so we only have that proton left. So you'll often hear people talk about protons being exchanged in acid-base reactions. On the other hand, we've got hydroxide ions, which are one of the main components of common bases. That's an oxygen bonded to a hydrogen. And with a complete octet on the oxygen with those free lone pairs, it controls 7 of the 8 electrons around it, sharing one of the electrons with the hydrogen. And that's one more than we expect from the position of oxygen in the periodic table. Goes to 6th element, so we expect it to just control 6 electrons. So that negative charge of hydroxide is specifically a charge on the oxygen itself. Now, hydrogen ions and hydroxide ions, when together in a reaction, will always seek each other out and combine together to produce water. This is a very vigorous, very spontaneous reaction. So regardless of who they came with to the party, if they find each other, they'll always bond, they'll always react. And for many years, we used to think, historically, that this was a sign of an acid-base reaction, a reaction that produced water. It's certainly commonly found in many acid-base reactions, the production of water, but it isn't always seen. Just because the reaction produces water doesn't mean it's an acid-base reaction. but it does give us a simple way of predicting the products for common acid-base reactions. Pick out the hydroxide from the base, pick out the hydrogen from the acid, they'll combine to produce water, and then the leftover bits, sodium and chloride, come together to form sodium chloride, the other product. Likewise, reacting phosphoric acid with potassium hydroxide, we take the hydroxide from the base, the hydrogen or one of the hydrogens from the acid, that gives us water, and then the leftover bits, which is now dihydrogen phosphate, and the potassium form potassium dihydrogen phosphate. So form water and then combine the leftovers. Similarly with nitric acid, take the hydrogen from nitric acid, the hydroxide from magnesium hydroxide. We actually need two hydrogens from the acid because we've got two of those hydroxide ions. So we need a hydrogen for both of those ions. We'll form two molecules of water, and the leftover bits, the magnesium and the nitrate, allows us to form magnesium nitrate as a side product. So if you're struggling, form water and then the leftover bits come together. That's a good start at predicting the products of an acid-base reaction. Now, it's also a good idea to become familiar with some of the common acids and bases, strong and weak, as we'll see here. The common strong acids in chemistry are when hydrogen combines with one of the halogens in group 7 that is not fluorine. So we're talking about hydrogen with chlorine to form hydrochloric acid, hydrogen with bromine to form hydrobromic acid, hydrogen with iodine to form hydroiodic acid. And then nitric acid using the nitrate ion with hydrogen, and sulfuric acid using sulfate with hydrogen are the other two common strong acids. The majority of our strong bases we find in a lab tend to be hydroxide containing compounds when they're paired with a group 1 metal, the alkali metals. We talked about this very briefly in chapter 2. Group 1 metals reacting very violently in water produce a strong base in hydrogen. So potassium hydroxide, sodium hydroxide, lithium hydroxide, etc. would be considered examples of strong bases. Now for some common weak acid and bases, carbonic acid is a good example using the carbonate ion with hydrogen. Also acetic acid, which is basically just vinegar, and then phosphoric acid, combining the phosphate ion with 3 hydrogens. That's the most commonly found weak acids. For bases, the commonly seen weak bases tend to be hydroxide with a group 2 metal, the earth metals. So magnesium and magnesium hydroxide, calcium and calcium hydroxide, and barium hydroxide. And into that mix, we'll just add ammonia, NH3, which is commonly seen in window glass cleaners. Most of the dirt that gets onto a window is acidic from your fingertips, and so we use a mild base to neutralize it and turn it into a water-soluble salt. Now keep in mind that when we talk about hydrogen ions in aqueous solution, that's incorrect because the hydrogen ion is not really very stable in water. What actually happens is that these hydrogen ions piggyback onto a molecule of water to form hydronium ions, H3O+. That's a true source of acidity in water, but you'll often find that textbooks just talk about hydrogen ions when they should really be talking about hydronium ions. Just be careful of that. So what makes a good acid and what makes for a good base? Well, there are many different definitions of acids and bases. The one that we're going to focus on is the Bronsted-Lowry theory. The Bronsted-Lowry theory tells us that an acid is a chemical which donates protons during the course of the reaction. So we look for the chemical at the beginning and then ask ourselves, how does that chemical formula change by the end of the reaction? In this case, a forward reaction, starting with the perchloric acid HClO4. It finishes as just ClO4. So it has donated a proton, which makes the perchloric acid indeed an acid. The water, on the other hand, by the end of the reaction, has picked up a proton. We'll talk about that in a minute. So for each chemical, ask yourself, what is about to happen? Is it a proton donator? Then it's an acid. We can see this from the Lewis structures here for the molecules. And it's this polar covalent oxygen to hydrogen bond. A much greater electronegativity in the oxygen, so that bond can easily break as molecules collide. The electrons retreat to the more electronegative oxygen, which is how bonds normally break. When they break the bonds, the electrons go to the more electronegative element because it's already got a larger slice of that electron density anyway. We break that bond, and the proton is transferred, donated to the molecule of water. We produce the hydronium ion that we were talking about. Now, specifically because the perchloric acid is giving away just one proton, we talk about perchloric acid as a monoprotic acid, a single proton donator. Other monoprotic acids that we should be familiar with include HCl, hydrochloric acid, and HNO3, nitric acid, giving away exactly one proton each time. And you can see again that oxygen to hydrogen bond, that vulnerable polarized bond. The more the bond is polarized, the weaker the bond becomes, the easier it is for it to donate a proton. So oxygen to hydrogen bonds are quite often the culprit in the acidity of molecules. So acids that give away one proton. We also want to study a couple of acids which are considered diprotic. That is, that they give away two protons in total. Let me get my annotation tools here. Put them up there. Okay, so carbonic acid is a good example. It's a relatively weaker acid. We can see that from the equilibrium constant, which is a lot smaller, 10 to the minus 7. But when it does give away multiple protons, it gives them away one at a time. We see individual steps for each proton donation. So the bond breaks, the electrons retreat back to the more electronegative oxygen, and that proton is donated, transferred to the molecule of water as we produce hydronium ions. It's not terribly good at it with a relatively small equilibrium constant, but when it tries to give away a second proton here, we can see for the forward reaction, the equilibrium constant is now dropped down to 10 to the minus 11, 4 orders of magnitude smaller. So although a relatively modest number of molecules gave away that first proton, an even smaller number of molecules of the hydrogen carbonate give away the second proton. We find this with all acids which can give away multiple protons. Each proton donation makes the next one progressively harder. So very few of the molecules will actually successfully give away both protons. So that's carbonic, H2CO3. We can also look at sulfuric acid. Whoop, still got my markings up there. There we go. And so in a very similar vein, we see each proton donation as an individual step. Sulfuric acid is a strong acid, so that first proton donation has a strong value for the Ka, 10 to the minus 2. That's pretty good in dilute aqueous solutions. So that first proton transferred over to a molecule of water. But even with a strong acid like sulfuric acid, giving away a second proton is harder. We can see that because the equilibrium constant is diminished, now just 1.1 times 10 to the negative 2. So it hasn't diminished much, but again, fewer molecules this time give away that second proton. And this is true for any acid. It gets tougher to give away each proton successfully. If we look at, let's see, triprotic acids for a second, only one I want you to be roughly familiar with is phosphoric acid, H3PO4, which can give away 1, 2, 3 protons in total. But again, we think about that donation, 1 proton at a time, and we have our own individual steps. Phosphoric acid, that first proton, a value of 10 to the minus 3 for the equilibrium constant. Giving away that second proton, the value goes down to 10 to the minus 8. Giving away that third proton, we go down to 4.2 times 10 to the minus 13. So very few of the molecules successfully give away that third and final proton to make a phosphate ion. It gets harder and harder to give the protons away. So that's the only ones I want you to be especially familiar with. Monoprotic acids like nitric acid, hydrochloric acid, and perchloric acid. Diprotic acids like sulfuric acid and carbonic acid. Triprotic acid like the phosphoric acid. The acids are our proton donators. On the other hand, the bases are our proton acceptors. And when a hydroxide containing base accepts a proton, as we had alluded to earlier, it picks up that proton and forms water, and then the potassium bit falls off. And it combines with the leftover bit of the acid, so we get potassium chloride as a side product. Similarly with lithium hydroxide, the hydroxide ion picks up the proton from the acid, we form water, and then usually in the right proportions, the leftover bits come together. Okay. We can also form this trick with chemicals like ammonia. Ammonia picking up a proton from water this time. Water can act as like an acid. And so the common thread we see through this for these bases, potassium hydroxide, lithium hydroxide, and ammonia, is that they're always accepting a proton during the acid-base reaction. And this is what Bronsted-Lowry is telling us. Bases are proton acceptors. So if an acid is a proton donator and a base is a proton acceptor, then the Bronsted-Lowry theory is ultimately telling us that an acid-base reaction is a proton transfer from the acid to the base each time. Let's switch tacks for a second and look at the naming of acids in chemistry. Oh, how much of that did you hear? I bet you didn't hear any of that, did you? I'm going to have to do that again because you just could see my lips moving. Okay, so back talking about the acids and bases. At least I caught that quick. With these acids and bases, for the naming of the acids, we look at the non-hydrogen part of the chemical formula. And that can be one of three things. It could be a non-metal, or it could be a polyatomic, specifically a polyatomic that ends in ITE, ite, or ATE, ate. And we treat or evaluate the name of the acid in one of three different ways, depending on what that non-hydrogen chemical in the formula is. So if it's just a simple non-metal ion from one of the elements in the periodic table, because those normally end in IDE, like chloride for chlorine, or fluoride for fluorine, we're going to base the name of the acid on that non-hydrogen, non-metal ion, but we'll stick hydro at the beginning of the name. We'll then use the name of the non-metal, but we'll change the name ending, IDE, to ic acid. So the acid based on the chloride ion becomes hydrochloric acid. The acid based on the fluoride ion becomes hydrofluoric acid. So we've just a simple non-metal, begin with hydro and finish with ic acid using the non-metal ion's name. Now, if we are facing one of those polyatomics, and specifically one of the polyatomics with a greater amount of oxygen, which would give an ATE ending to the name of the polyatomic, so things like SO4 sulfate or PO4 phosphate, this time again using the name of the polyatomic ion, but we'll take off the ate ending and change it to ic acid. So the sulfate acid becomes sulfuric acid. The phosphate acid becomes phosphoric acid. Finally, if the polyatomic in the formula would have an ITE ending, like NO2, which is nitrite, or ClO2, which is chlorite, we'll base the name of the acid on that polyatomic ion, but we'll take off the ITE ending and change it to us acid. So with nitrite, we'll make it nitrous acid. With chlorite, we'll make it chlorous acid. Again, revising and looking back at the table of polyatomic ions from chapter 3 would be a good idea. Now, with a little bit more thought, we can actually start predicting more accurately what the products of an acid-base reaction will be based on the base that's in the acid-base reaction. We already know a bit of this tonight because it was said that hydroxide-containing compounds would scavenge for hydrogen in the acid to produce water. And having done so, the leftover bits, potassium and chlorine, would come together to form potassium chloride. Or nitric acid with calcium hydroxide, the hydroxide looking for a hydrogen to form water. There's two of those hydroxide ions, so they're looking for two hydrogens, two protons, so we need a second molecule of the acid to balance the equation. We form two molecules of water, and again the leftover bits come together. That's the calcium in calcium hydroxide and the nitrate and the nitric acid. Then the hydroxide, again combining with hydrogen from the acid. We form water, two molecules, and then the chlorate ion and the barium ion left behind come together to form barium chlorate. There's a second rule of thumb for recognizing the products, but this time it's based on the base being used containing hydrogen carbonate, HCl3. Now it's trying to do the same thing that the hydroxide was doing. It's trying to find and scavenge for hydrogen from the acid. But this time, picking up that proton, that hydrogen, and adding it to HCl3, we now have H2Cl3, and we use those pieces to form two of our three products, carbon dioxide and water. So this H2Cl3 isn't physically made, not even for a second. It's just giving us the bits we need so we can produce carbon dioxide and water each time. The CO2 and H2O produced, the remaining bits, as we saw before, in this case the potassium and the chlorine, come together to produce the last and third product, potassium chloride. So we produce potassium chloride, water, and carbon dioxide. Second example, again, hydrogen carbonate. Just like the hydroxide was, is looking for a hydrogen from the acid. There's two of these hydrogen carbonate ions, so they need two hydrogens, one apiece. So we use 2 molecules of water. That forms H2CO3. And with that formula, it lets us produce the CO2 and the H2O, carbon dioxide and water. Once sorted, the leftover bits, magnesium and nitrate, form our final product, magnesium nitrate, in the final balanced equation. So the hydroxide ions scavenge for hydrogen to produce water. The hydrogen carbonate ions scavenge for hydrogen to produce water and carbon dioxide. Finally, the base might be based on the carbonate ion, CO3. And it wants to do exactly the same thing that hydrogen carbonate was doing, picking up protons so it can briefly form H2CO3. But of course the CO3, the carbonate, needs to pick up 2 protons. Picks up the 2, we form the CO2 and water again, and the leftover bits, calcium and sulfate, form calcium sulfate. And we get our 3 final products again. So hydroxide ions pick up hydrogens to form water. We then combine the leftover bits. Hydrogen carbonate picks up hydrogen to form water and carbon dioxide. And then the leftover bits come together. And then finally, carbonate combines with 2 hydrogens, either getting them from 1 molecule of acid or getting them from 2. Picks up those 2 hydrogens so it can form carbon dioxide and water again, and then the leftover bits form that third and final product. Let's take a look at some examples and try these for yourself. Predict the product of these 4 acid-base reactions. Okay, let's see how we're doing with these ones. So in the first one, we have got a hydroxide containing base, and that picks up a hydrogen to form water, H2O. We then pick up the leftover bits, lithium metal and nitrate non-metal, the polyatomic, so we form lithium nitrate as the remaining product. Lithium plus 1 ion, nitrate a 1 minus. Just as we did in chapter 3, make sure the charges cancel out. Next one, this time it's hydrogen carbonate. So in our minds, we're trying to put the pieces together to form H2CO3. That isn't actually produced, but once we scavenge those pieces, which needs just 1 more hydrogen, we can use that to make water and carbon dioxide. And then the leftover bits give us our final product, sodium and chlorine, for sodium chloride. Next one, this time carbonate for the base. Again, we're trying to form the H2CO3, but we're going to need both of those hydrogens from the acid. It gives us the H2CO3 formula, so it gives us H2O and carbon dioxide. And then our leftover bits come together, the sulfate with the barium, so we produce barium sulfate. Last one, back to a hydroxide containing compound. So we're looking to nick one hydrogen each time, although there's two hydroxide ions, so we'd need a second molecule of the chloric acid to give us a second hydrogen, a second proton. That would allow us to form two molecules of water. And then the leftover bits again come together, the magnesium and the chlorate ion. So we'd produce magnesium chlorate, Mg2 plus, chlorate 1 minus, so we need two of them to cancel out with the magnesium charge. Okay. Okay, so that's where lecture on campus finished today, but I want to do a little bit more just to make sure that we get pretty much the chapter finished by the end of next week, which will take us to Thanksgiving break. And so after Thanksgiving, we should be pretty much focused on chapter 10, the last chapter. It's a pretty small chapter in terms of lecture notes, so we should have time in that very last week to be focused on revision come Thursday and Friday. So we want to lead into this idea of acid-base reactions being normally reversible systems and how these reversible systems form conjugate pairs. Now remember, the position of equilibrium tells us which of the two reactions is working harder. The two reactions are now working at the same rate when equilibrium is established, and so you quite often see the equilibrium arrows equal in length, but it doesn't mean that they're equal in concentrations. Quite often when equilibrium is established, one of the two reactions had the upper hand. We either had mostly products on the right, that's products formed by the forward reaction, and we would say in chapter 6 that the forward reaction was favoured. So used up most of these chemicals, produced mostly these chemicals when equilibrium was locked in. We'd say that the forward reaction had been working harder, the forward reaction was favoured. Now for the acid and base being used in that forward reaction, if equilibrium is on the right, we'll say that these acids and bases driving the forward reaction are strong acids and bases. But remember, there's a competing back reaction. And normally that back reaction is also an acid-base reaction doing its own proton transfer, transferring the proton back to form the original materials. And so acid-base reactions are normally reversible. And just as we saw in chapter 6 of equilibrium chemistry, we're therefore talking about two competing acid-base reactions. So if the forward reaction is favoured, if the forward acid and base are strong, then it means that the chemicals in the back reaction forming an acid and base must be weak acid and bases, because they're not very good at transferring a proton. They're not very good at driving the back reaction. Conversely, if the position of equilibrium is on the left, we would say in chapter 6 that that was the back reaction working harder. That was the back reaction favored, with mostly the chemicals on the left being produced, and we'd used up most of the chemicals on the right. So for those chemicals on the right which are working harder, in this case they would be a strong acid and base. So just like any equilibrium system, only one of the two reactions can be favored when equilibrium is established, which means that one of the reactions will be referred to as a reaction between the strong acid and base, and one reaction will be referred to as the reaction between the weak acid and base. But let's take a look at some examples and you'll see what I mean. So let's see, HNO3 with water to produce NO3 and H3O+. As we look at the reaction from left to right, notice that the HNO3 finishes as NO3. We can recognize it at the end because it still has the nitrogen and the oxygens. Over the course of that reaction, to go from HNO3 to NO3, it's donated its proton. So the HNO3 is acting like an acid. And these two chemicals across the equilibrium system are related to each other because of the presence or absence of that proton. And two chemicals in a system like this, which are almost identical and only differ by the presence or absence of a proton, are often referred to as conjugate pairs. Only the presence or absence of a proton separates them. There should be no other changes other than that proton being present or not. So we know that the HNO3 nitric acid is indeed an acid. A proton being transferred from the nitric acid to the water. But if that water is picking up a proton, then it's playing the role, playing the part of a base. And we can see that in the forward reaction because the water finishes up as H3O+. Look at how it starts, look at how it finishes. It's picking up a proton, the proton that the acid is donating. And we can see that for the H2O and the H3O+, again, their chemical formulas only differ by the presence or absence of a proton. So H2O and H3O+ can also be considered a conjugate pair. We normally see reversible acid-base reactions being linked in this way. There's a proton transfer in the forward reaction, and each chemical turns into its conjugate partner. But for the back reaction, if we look at the water here, the H3O plus the hydronium ion, to turn back into its partner, going from H3O to H2O, it's got to pick up a proton. It's got to donate a proton, I beg your pardon there, getting ahead of myself. And so donating a proton, it's an acid. Starts at H3O plus, finishes as H2O in the back reaction. And then the conjugate form of our acid, the HNO3, conjugate form NO3, in the back reaction What happens to it? Well, it starts as NO3, it finishes as HNO3. It's about to pick up a proton. If it's about to pick up a proton, it's acting as a base. So both forward and back reactions are proton transfers. Transfers from an acid to a base, from an acid to a base. And for each conjugate pair in the system, which only differ by the presence or absence of a proton, those conjugate pairs contain an acid and a base. An acid and a base. So you'll always know that one of the conjugates is an acid and one of them is a base. And if we look at the implied position of equilibrium, with the arrow from left to the right being longer, it's telling us that the forward reaction is favoured. It's telling us that the HNO3 is very good at its job of giving away a proton. And if it's good at giving away a proton, it can therefore be termed as a strong acid. Likewise with the water, it's part of that favoured forward reaction. And so if it's very good at its job of picking up protons, it's a strong base. Let me just give myself a bit of room here. Make it a bit less cluttered. And this is typical of the favoured acid-base reaction. It's a reaction between a strong acid and a strong base. Meanwhile, the competing back reaction, which we can see as the less favoured reaction, the nitrate obviously is swimming against the stream. It has a hard job of picking up that proton, and so the nitrate is a relatively weak base. I get my pen to work here. Likewise with the hydronium ions, H3O+. They're swimming against the current from right to left because it's a forward reaction which is favoured. And so they can't be very good at their job of giving away protons. It's therefore a relatively weak acid. So we've got an acid-base reaction in both directions. Normally the strong acid reacts with the strong base, and in the unfavoured reaction, the weak acid reacts with the weak base. Let's take a look at another. Just clear my screen here. Again, I'll just give myself some room. So let's look at the reaction. Actually, I've moved it in the wrong direction here. That's the bit I want to get cleaned up. I'm on the wrong side. There we go. So if we look at the chemicals we have in play here, the CH3COOH, looking for its conjugate partner across the reaction. There it is there, the CH3COO. We notice its conjugate. Right, everybody hear me still? My headphones have given up on me again. They must be low on charge. Let's just test to make sure you're still hearing me. Boom, boom, boom. Hello. Okay. Always worries me a bit when the
headphone set kind of dies on me halfway through a recording. So apologies for the sound quality now, it's probably a bit down. If we look at a system here, we've got the acetic acid with the acetate ion. They definitely form a conjugate pair because they only differ by the presence or absence of a proton. We ask ourselves what each chemical does. In this case, it's about to give away the proton, which makes it an acid. And if we look at its conjugate, to get back to the original acid, it has to pick up a proton. It's acting as a base. So we get an acid-base conjugate pair. We can see from the direction of the arrows, the equilibrium arrows, it's the back reaction which is favoured. So the conjugate base is strong. Meanwhile, the acid, swimming against the current, so to speak, is a relatively weak acid. We then look at the other conjugate pair. Let's try a different colour. Let's try orange. Well, something better. To contrast, let's go purple. Not that it really matters. And the water, its conjugate partner is H3O plus again. And for the water, H2O, to turn into H3O, it's got to pick up a proton. It's a base. It's part of the unfavoured forward reaction, so it's a relatively weak base. Here's a proton transfer in the forward reaction from the acetic acid to the water. Its conjugate partner, hydronium, it starts like this, and to get back to water, it's got to give away a proton. It's acting as an acid, and it's part of the favoured back reaction, so it's a relatively strong acid, giving that proton to the acetate. Yeah, for completeness. So with a conjugate pair, if we have a strong acid, its conjugate partner is where am I? I'm on the wrong side. If we have a strong acid, its conjugate partner is a weak base. And if we have a weak acid, its conjugate partner is a strong base. The conjugate pair are part of opposing, competing reactions from left to right and right to left. So only one of them can be winning. Only one of them can be good at their job. So if the acid is strong, the conjugate base is weak. If the acid is weak, the conjugate base is strong. And so as we look at the entire system, we've got one weak acid, one weak base, one strong base, one strong acid. We get a complete set, so to speak. Okay, let's try a couple more before we call it a day. Here's another one which has been worked out for us. Again, looking at the system, just pick a conjugate pair out. In this case, I've started with the NH3 and its conjugate partner NH4. We know they're a conjugate pair because they only differ by the presence or absence of a proton. So we can physically link them up. And then we ask ourselves, what does the NH3 have to do to turn into NH4? Well, it has to pick up a proton. Bases pick up protons, while the NH4, to turn back into its conjugate partner, it's got to give away a proton, so it's an acid. Not only that, but as we look at the equilibrium arrows, the longer arrow is pointing from left to right. The forward reaction from left to right is the favoured reaction. And so that base is part of the forward reaction, which is favoured. It's therefore the strong base. And the NH4, the acid in the conjugate pair, is part of the unfavored back reaction, so it's the weak acid. Strong base is always paired with a weak acid. Look at our second conjugate pair, the H2SO4 and the HSO4, 1 minus. For the H2SO4 to turn into its conjugate, it needs to give away a proton, giving away a proton to the chemical it's reacting with, the NH3 of course. So the actual reaction here is a proton transfer like this. Picking up the proton is of course a strong base, giving away the proton, and the forward reaction is a strong acid, which means its conjugate partner is a base. It's working with the unfavored back reaction, so a weak base. We can see that's true, that HSO4 about to pick up a proton from the NH4, which is exactly what we expect a base to do. Let's try, I think maybe 2 more on the next page. Let's take a look. Oh, I'm getting thirsty and tired. Oh, second one, I've done it all in one job here, one lot. As we break it up, the HCl3 has a conjugate partner of Cl3 because the conjugate's formula is only allowed to change by having more or less protons. And the HCl3, in order to turn into Cl3, has got to give away a proton. It's acting like an acid. It's part of the unfavored forward reaction, so it's a weak acid. And the Cl3 turning back into its conjugate has to pick up a proton. It's a strong base in the favored back reaction, picking up the proton from the HSO4. The HSO4, to turn back into its conjugate, has to give away a proton, so it's a strong acid because it's part of the favored back reaction. And the SO4 in the forward reaction needs to pick up a proton, but it's not very good at it because it's part of the unfavored back reaction. Sorry, the unfavored forward reaction, I beg your pardon. So it's a relatively weak base. Take a couple of minutes and try the next one. The perchlorate ion with the H2PO4 dihydrogen phosphate turning into HClO4 and the HPO4 2 minus. Identify the conjugate pairs. Identify them as either donating or accepting protons, either acid or base, and with the implied position of equilibrium, recognize them as strong or weak acids. Take a minute of Zen to work that out. All right, let's finish with this one. So let's start with the ClO4 on the left and look for its conjugate. That conjugate is the HClO4. The chemical formula only differs by the presence of the proton at the end here. Now ask ourselves, what does the ClO4 have to do to become HClO4? Well, it's got to pick up a proton. The chemicals that pick up protons in the course of a reaction are bases. Is it a favored process from left to right? No, it's a shorter arrow. So the forward reaction is unfavored. This base is a pretty poor base or a weak base. Meanwhile, its conjugate, to turn back into the ClO4, it's got to get rid of that hydrogen, got to donate a proton. It's an acid. But it's now part of the favored flow of traffic, the favored back reaction. And so it must be good at its job. And it's a relatively strong acid. Looking at the other conjugate pair, easy to spot. The H2PO4 and the PO4. So what does the H2PO4 have to do to turn into its conjugate? It's got to give away, donate a proton. It's an acid. Again, it's swimming against the current as part of the unfavored reaction from left to right. So it's a relatively weak acid. Meanwhile, its partner, the HPO4, to turn back into the original H2PO4, it's got to pick up a proton. It's a base. And it's part of the favored back reaction from right to left. It's a strong base. There you have it, your two conjugate pairs and their acid and base designations and their relative strong and weak acid and base designations. There'll always be exactly one strong acid, one strong base, and one weak base, and one weak acid. Normally, the favoured reaction is the reaction between the strong acid and the strong base. The acid good at giving away the proton, the base good at accepting, and that's driving equilibrium with the back reaction in this case, the favoured reaction. Okay, that's enough acid-base torture for one night. I'll see everybody again on YouTube on Monday evening.